Do you guys have any idea about the mysterious thing captured by the James Webb Telescope? Well, it appears to be the binary star system. In today's video, we will be talking about the JWST and binary star system. The James Webb Space Telescope captured an incredible shot of a single star using all 18 mirrors, proving that the spacecraft can now view starlight. The new image shows 18 unfocused duplicates of a single sun-like star, named HD 84406, in the constellation Ursa Major, arranged in a hexagonal pattern similar to James Webb's primary mirror's honeycomb structure. The initial step of aligning James Webb's 21-foot primary mirror, which comprises 18 hexagonal pieces of gold-plated beryllium metal, is captured in this magnificent image. Next, the telescope will focus on 18 photos before aligning them into the star's single prominent appearance. Last month, the James Webb Space Telescope launched from the Guiana Space Center on Christmas Day and nestled into an orbit 1 million miles from Earth. The observatory, which cost $10 billion, is presently undergoing a 3-month alignment procedure before it can begin observing the universe. NASA describes the new snapshot as an image array in a recently released post. All 18 primary mirror segments reflect light from the star at the telescope's secondary mirror and into the near-infrared camera's primary camera, NIRCam. The team rotated each of Webb's 18 primary mirror segments to put 18 unfocused duplicates of a single star into a predetermined hexagonal shape, NASA stated. Now that the image array is complete, the team moves on to the second alignment step, known as segment alignment. The James Webb engineers on the ground will change the secondary mirror alignment during the segment alignment phase to make each dot of starlight more concentrated. After this global alignment, the team will go on to the next phase, which is image stacking, which will stack 18 points of light on top of each other to generate one HD 84406 composite. We direct the segment dots into this array to have the same relative placements as the actual mirrors, explained Matthew Lalo, a systems scientist at the Space Telescope Science Institute, James Webb's Mission Operations Center. This familiar structure allows the wavefront team an easy and natural method of seeing changes in the segment locations in the context of the complete main mirror during global alignment and image stacking. Now, we can observe the primary mirror develop into its exact desired shape. Each dot of starlight is tagged with the accompanying mirror segment that recorded it in another version of the new image. James Webb returned its first ever photographs earlier this month, including a photo of its primary mirror and HD 84406, but in a messy, disorganized mosaic. As it stands, James Webb's photographs will not be as beautiful as those captured by identical space telescopes like Hubble. According to the space agency, the pictures are fuzzy because they were shot as part of the telescope's fine-tuning procedure. Regardless, it continues to make them available to the general public. NIRCam, near-infrared camera, an infrared imager from the edge of the visible to the near-infrared, is one of the James Webb Space Telescope's instruments. The NIR-SPEC, near-infrared spectrograph, will also conduct spectroscopy in the same wavelength range. MIRI, mid-infrared instrument, will measure wavelengths ranging from 5 to 27 micrometers in the mid to long infrared spectrum. The fine guidance sensor, near-infrared imager, and slitless spectrograph keep the observatory's line of sight stable during science investigations. At the beginning of February, NASA announced that it had caught the first photons of starlight, a milestone known as first light. This milestone represents the first of many steps toward capturing initially unfocused photos and using them to fine-tune the telescope, NASA noted. Though the procedure is still in its early stages, the initial results are consistent with predictions and simulations. Since its launch on Christmas Day from the European Space Agency's spaceport in French Guiana, the James Webb Space Telescope has worked flawlessly. When it launched, Webb had to be folded up to fit inside the Ariane 5 rocket because its size was more significant than a tennis court when fully deployed. However, the telescope deployed all of its mirrors last month and it arrived at its parking position at Lagrange Point 2. a zone of balanced gravity between the Sun and the Earth a few days later. About 260 light-years away, HD 84406 is a Sun-like star near the Big Dipper. Once the telescope comes into focus, it will be too bright to analyze with WEBB, but it is a suitable calibration target. Its surface temperature is around 5000 K, or 8,540 degrees Fahrenheit, instead of the Sun's 5,778 K, or 9,940 degrees Fahrenheit. According to data from the ESA Gaia telescope, it is around 4.4 times the size of the Sun and 11 times more bright, and it may be part of a binary pair. If it's binary system, the smaller star is most likely a red dwarf around half the size of the Sun, with the primary roughly 3 billion years old, making it slightly younger than the Sun. James Webb began development in 1996 and was scheduled to debut in 2007. However, a substantial overhaul in 2005 pushed the release date back. Construction was ultimately finished in 2016 and significant testing work began. However, the COVID pandemic caused a delay, and the launch that was initially slated for March 2021 was pushed back to October and then December. Slated to launch on December 18, 2021, it was then postponed again due to an event during launch preparations. After being delayed for Christmas Eve, the launch was eventually pushed to December 25th. Nevertheless, now JWST is capturing every strange thing around the cosmos. Planets with two parent stars are subjected to a twofold radiation dose, making them significantly less favorable for life than single star systems. However, looks may be misleading. According to a new study, a pair of correctly positioned parent stars gravitational arm wrestling should create a magnetically shielded habitable zone for an orbiting brood. When thinking about the habitability of a major proportion of the stars in the galaxy that are in binary systems that might give increased habitability conditions, astronomer Jorge Zulaga of the University of Antigua in Colombia told Discovery News. The influence of a pair of circling stars on each other's speeds of rotation, which determines how magnetically active they are, was studied by Zulaga and colleagues. The specifics vary depending on the size and separation of the two stars. Still, computer models reveal that there might be magnetically calm areas surrounding binary stars, a discovery that dramatically increases their habitable zones, orbits where water could persist on a planet's surface. Although water is essential for life, it is not the sole component. For example, while being in the Sun's habitable zone, Venus and Mars in our solar system currently lack life-friendly atmospheres. Increased solar activity from a young Sun might be partially or entirely to blame for Venus and Mars's divergent evolution from Earth. But, according to the new research, the Sun's early violent outbursts could have been tempered if it had a suitable partner star. It's not enough to be in a star's habitable zone to be habitable. Other aspects must be taken into account. For example, it must include, from the beginning of the stellar life, the star's magnetic activity, the planet's magnetic protection, and the emission of a greater level of radiation, Zulaga explained. Researchers examined 6 binary systems with circling planets discovered by NASA's Kepler Space Observatory. Researchers discovered that 3 of the systems were well suited to having planets in habitable zones after considering the gravitational interactions of the stars. The investigation found that one system, Kepler 34, had a habitable zone almost devoid of harmful X-ray and intense ultraviolet radiation. This study introduces a novel concept. When two stars form a binary system, gravitational tidal forces exist, similar to how the moon pulls on Earth and generates the ocean tides. According to astronomer Paul Mason of the University of Texas in El Paso, this causes the stars' spins to slow down over time. It's nearly like marriage. They slow each other down since they are bonded together, which is excellent for rotating planets. Mason told Discovery News that it helps them hang on to their water. The research is available and will be published in the journal Letters shortly, an adapted version of a binary star as viewed from an orbiting planet. So what do you think about James Webb Telescope capturing binary star systems? Let us know your views in the comment section below, give us a thumbs up, and tell your friends about us if they are also interested in the same things you are. Finally, please subscribe if you would like to hear more on this regularly. We'll talk again soon.